Okay, lesson 1.7 is on inductive reasoning. This is used in a lot of algebra, but even more when you get to like geometry, inductive reasoning is used a lot. Okay, what is inductive reasoning? Use it every day without even really know you're using it. Okay, and what inductive reasoning is, it's making a conclusion based on any pattern you observe. Okay. Now, what we do is we take the inductive reasoning that's naturally in our head and we basically make a conjecture. And a conjecture is a conclusion you reach by inductive reasoning. Okay. So let's show what inductive reasoning is and how to come up with conjectures and prove if they're true or false. Okay. First example, use inductive reasoning. Make a conjecture about the next figure in the pattern, then draw the figure. Okay, so as we look at each figure, the only difference is this yellow triangle is in a different spot. And if you see, what do we notice? All right, we're using inductive reasoning to show that all it is rotating around the square. So now that we've determined the pattern, what we do is we can go ahead and we can redraw this pattern. My artistic skills are quite awful. And draw that in. Okay, so that would be the next figure in the pattern. Okay, you go ahead and try the next, pause the video, try the next one on your own. Okay, so this next you try. You notice we have a circle in each of these diagrams. And what do we notice? This figure has 3 sides, this figure has 4, this figure has 1, 2, 3, 4, 5 sides. So now we're using inductive reasoning that to make a conjecture that we're adding, right? We are adding a side to the polygon inside, okay? So now our next one will have 6 sides. And again, do not knock the artistic skills. All right. So now, not only do we use it for diagrams, but we use inductive reasoning to look for number patterns. Okay. So use inductive reasoning to write a rule for each number pattern. Then write the next 2 terms of the sequence. So this is what we call a sequence. It's basically a set of numbers that have a pattern. And if you notice here, we go from 30 to 25 to 20 to 15. What is happening each time here? Well, you should notice you're subtracting 5. So basically, the rule is you are subtracting 5 each time. So if we wanted to find the next 2 terms in the sequence, 15 minus 5 would be 10. 10 minus 5 would be 5. Okay, example 2. We have 2, negative 2, 2, negative 2. Okay, what do we see happening here? Well, I like to say we're multiplying by negative 1 each time, right? So if we're multiplying by negative 1, 2 times negative 1 is negative 2. Negative 2 times negative 1 is 2. All right, so you could say you're multiplying by negative 1 each time, or you're going to say it's just a number and its opposite each time. So the next one in the pattern would be 2 and then negative 2. Okay. Now example 3 picks up a little bit, right? It's a little more difficult of a pattern to recognize. Okay, so we go from 1 to 3, 3 to 4, 4 to 12, 12 to 13. If you look, you're not adding the same amount. You're not multiplying by the same amount each time. So now you have to put some operations together. So if I look here, right here, I notice 1 and 3 is times 3, and 4 and 12 is times 3. But what's happening in between? Well, if I look at 3 and 4, 12 and 13, that goes up 1. So what's happening is you're basically multiplying by 3 and then adding 1. So one time you'll multiply by 3, then you'll add 1 to that answer. So 1 times 3 is 3, 3 plus 1 is 4, 4 times 3 is 12, 12 plus 1 is 13. So now we're on the multiply by 3. Multiply by 3, you get 39. Now we're going to add 1 to get 40. All right. So do me a favor, do the 3 you tries down below, and then come check your answers. So the first you try here, what do we notice is happening here, right? We are adding 5 each time. So the rule is you're adding 5 each time, and now the next two terms of the sequence would be 19 plus 5 is 24, 24 plus 5 is 29. You try number 2. What do we notice? 3 to 9, 9 to 27, 27 to 81. You know you're definitely not adding the same amount each time. So, am I multiplying by the same amount? Yes, I'm multiplying each one by 3. And that would be the rule. Multiply by 3. So the next one would be 243. And then 243 times 3 would be 729. And the third you try. Again, this is a tricky one. You go from 1 to 1, 1 to 2, 2 to 3, 3 to 5, 5 to 8. What is the pattern going on here? Okay. Well, what you should notice is here you went up 0, here you went up 1, here you went up 1, here you went up 2, here you went up 3, right? So you're seeing some addition. So what are we doing here? Is there really a pattern with that, right? No. Okay. So what you notice is if you had a previous number here, it'd probably be 0. So 1 plus 0 would give us 1. Now if I add these two numbers, 1 plus 1 is 2. Now 2 plus 1 is 3. So the rule is you're basically adding the two previous numbers together. So 2 plus 3 is 5, 3 plus 5 is 8, 8 plus 5, this is now going to be 13, and then 8 plus 13 would be 21. Okay. Now, inductive reasoning brings us to how can we determine if a conjecture is true or false? Now, if a conjecture is true, all you have to do is write true. And for every example you can create for that conjecture, it must always be true. If you can come up with one false example, which is known as a counter example, this is an example that proves a statement is false. All right, it needs to follow a conjecture that is false. For example, right? Every four-sided figure is a rectangle. This here is the conjecture. And we want to determine if this is always true. And as you can see, I can draw any four-sided figure, but does that mean it's a rectangle? No, right? So this conjecture is false. And this four-sided figure I drew that's not a rectangle would be your counterexample. Okay? Now, conjectures, like I said, can be true or false. So number 2, the absolute value of any integer is positive. Okay? Well, if I take the absolute value of any positive number, what is it? Positive. The absolute value of any negative number is positive. So can you come up with an absolute value of any number and it be negative? No. That means this is true. Okay. Example 3. The next figure in the diagram has 15 dots. All right, well, let's look at the pattern. 1 dot, 3 dots, 6 dots, 10 dots. So what is happening here, right? Well, if we come up with the pattern here, right, you're not multiplying by the same number, so what's happening here is you're adding 2. How many did you go up here? 3. How many did you go up here? 4. So I notice I'm going up 1 more each time. So the next one I know I'm going to go up 5, which would give me 15 dots. So this conjecture would also be true. Okay? Do the 3 you try problems and then come back and check your answers. So you try 1. The last digit of the product of 5 and a whole number is either 5 or 0 or 5. So product, you have to know, means multiplication. Okay? So if we take any number and multiply it by 5, 5 times 2, 5 times 3, 5 times 4, will your product, the answer, always end in a number whose last digit is 0 or 5? Yes, this is always true. Therefore, we'll write that that conjecture is true. Okay? Every triangle has 3 sides of equal lengths. Is that true or false? Right? You probably said false, and you're right, but you can't stop there. Provide a counterexample. Right? There's a triangle, and all 3 sides are definitely not equal. And you try 3. The opposite of a number is always negative. Okay? Well, if I look at it, if I just think about that, that's going to be false. And any counterexample, you can come up with any. If I take -4, what's the opposite of that? Opposite of -4 is +4. So that is a counterexample that shows that this is not always true. Okay, so go work on the practice worksheets, and it is Friday, so enjoy your weekend.